Welcome to lesson 3 of 4 in this tutorial, covering energy changes in systems. This is the third in a series of 4 lessons covering the topic energy changes in a system. In the last lesson, we learnt about how to calculate energy changes. We are now able to use formulae and apply them to different calculations. Here are our key learning objectives for this lesson. We will start off by looking at the formula for energy changes, move on to look at specific heat capacity of a liquid, and finally we will look at the specific heat capacity of a solid. Here are the AQA specification points for this tutorial. Pause the video now to have a read through them before we begin. We'll start by looking at how to work out the amount of heat energy lost from a system. We can calculate the amount of energy that is stored in or released from a system using the following equation. This will tell us the heat energy transferred in a particular reaction, whether it has been lost or gained. The equation is change in thermal energy is equal to the mass times the specific heat capacity times the temperature change. The short form, shown here, is acceptable to use in AQA exams, as long as you know what everything stands for. Take careful note of these units as well. You don't want to use the wrong ones in the exam. Most of them should be pretty familiar to you. We'll now fill out this table to help you become more familiar with the symbols in the equation we just learnt. Firstly, we'll start off with the symbol Q. This stands for the heat energy transferred. It is defined as the heat energy that can be lost or gained. And is the delta H of a reaction at constant pressure. The units are joules. Delta T is going to stand for the temperature change. This is defined as the temperature change of the water or the solution. The units are Kelvin. Next, we'll look at M. This stands for mass. This is defined as the mass that has undergone the temperature change. The units for mass are grams. Finally, we'll look at the term C. This stands for the specific heat capacity of water. It's defined as the amount of energy needed to raise the temperature of 1 kilogram of water by 1 Kelvin. The units for this are joules per gram per Kelvin. This is a completed table. It's a good idea for you to take a note of this, as this will help you to use the equation in the exam. The amount of heat energy needed to increase the temperature by 1 degree Celsius depends on the type of liquid and the mass of the liquid. For example, it might take a different amount of heat energy to increase the temperature of a beaker of oil compared to a beaker of water. Also, it takes more energy to increase the temperature of a mass of water that is larger. For example, this bath would take more energy to heat than this small beaker. Some liquids need lots of energy to increase the temperature by 1 degree Celsius, whereas other liquids need less. Each liquid has a specific heat capacity, which tells us how hard it might be to heat up. The higher the specific heat capacity, the higher the temperature that will be needed. The symbol that stands as a triangle simply means change in. Therefore, delta E simply means the change in energy. In AQA exams, the value for specific heat capacity will be given in the question. However, it is useful to remember that the specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Let's have a go at this practice question. Pause the video now to attempt it by yourself before we go through it step by step. The answer to this question is 2,880 kilojoules. First, we need to write out the equation for specific heat capacity. As we've just seen, this will be delta E is equal to mc delta T. Now we can calculate the temperature change. We have not been told the value in the question, so we need to work it out. So from the question, we know that she heats it all the way up to 65 degrees, and she started at 20 degrees. This means that the temperature change must be 45 degrees. Finally, we can use the formula. We now have all the numbers that we need, so we can simply substitute them into the formula. When we give our final answer, it may be more appropriate to give the units in terms of kilojoules. So here, we'll do our delta E equals mc delta T to remind ourselves of the formula, and then we'll just substitute the numbers in, so we'll put 20 times 45 times 3200, which gives us an answer of 28. So let's have a go at another practice question. Try it yourself before we go through it together. The answer to this question is minus 480 kilojoules per mole. Let's work through it together step by step and see how we got there. First, we need to write out the equation for specific heat capacity and fill in the values that we know. So here we need to write out our equation, which is Q equals mc delta T. And then we can say we don't know what Q is. Our N is 100 grams. C is 4.18. And delta T we need to work out, which is going to be 348 minus 293, which gives us a value of 55. Now we can calculate the heat energy transferred. So here we need to do Q equals our mass, which is 100, times C, which is 4.18, times 55. This gives us an answer of 22,990, and this is in joules. Now we can convert the value of Q into kilojoules. So to do this, we simply do 22,990 divided by 1000. So this gives us an answer of 22.9 kilojoules. Now we will calculate the total number of moles of ethanol that was burnt in the reaction. To find the number of moles, we use the formula we learnt earlier. So here we need to do moles is equal to mass divided by mR. So we know that our mass is going to be equal to 2.2. We can work out our mR, and that will come to 46.1. And therefore the number of moles is going to be 2.2 divided by 46.1. This gives us an answer of 0.04772. Finally, we can calculate the standard enthalpy change of combustion by dividing the value of Q in kilojoules by the number of moles of ethanol burnt. So here, right, the standard enthalpy of combustion is represented like this. So what we need to do is we need to put minus 22.9 over 0.047722, which we found here, and this will give us a value of minus 479.85. So we're going to say that it's equal to minus 480 kilojoules per mole to 3SF. Let's try another practice question before we move on. Pause the video here to attempt this question by yourself. Exam questions can ask you to evaluate the calorimetry value calculated during an experiment. The AQA specification doesn't ask you to know this next part about accuracy specifically, but it often comes up in calorimetry questions. Let's explore some of the reasons together. The first reason is that the energy may have been given off to the surroundings or used to heat the beaker itself, so the temperature change will be underestimated. The next reason is that the reaction might have been incomplete, so not all of reactant A has been converted into reactant B. Finally, the specific heat capacity values may not be exact or up to date. Also, the reactants may contain some impurities, which means that the specific heat capacity would vary slightly. When answers are very large, always think about simplifying units. In this case, we converted from joules to kilojoules. Sometimes, the question might specify which units they want the answer in, but if they don't, just work in whichever units are easiest for you. Let's move on to the next specification point, covering the specific heat capacity of a substance. When we calculated energy changes in the previous section, we used a value called the specific heat capacity. For AQA exams, we need to know its definition. This is shown here as the amount of energy required to raise the temperature of 1 kilogram of substance by 1 degree Celsius. It is different for each liquid. If a large amount of energy is required to heat up a substance, this means that the specific heat capacity will be very high, and the substance is able to store lots of energy. If a small amount of energy is required to heat up a substance, then its specific heat capacity will be very low, and the substance won't be able to store lots of energy. In AQA exams, the value for specific heat capacity will be given in the question. However, it is very useful to remember that the specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Let's move on to our final specification point, covering investigations into specific heat capacity. Measuring the specific heat capacity of a liquid is fairly simple. Let's quickly recap the definition of specific heat capacity. It is the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. We can rearrange this into specific heat capacity equals the change in thermal energy divided by the mass multiplied by the temperature change. Again, we can show here that there is a short version that is acceptable in exams. However, you still need to know what the symbols stand for. Here are the units for the equation, which we have already been through earlier in the lesson. We are also able to calculate the specific heat capacity of a solid material. This is a little more complicated, and there are various steps to this method, but you need to know the specific method. The first step is to take the block that we're going to investigate. The block is going to have two things embedded into it. The first is a thermometer. This will be used to measure the temperature of the block. And the second is an immersion heater. This is used to provide heat energy to the block. In this experiment, we are essentially seeing how much heat energy is needed to heat up the block to a certain temperature. We should next measure the mass of the block. This is done using a top pan balance, and we should ensure that we record the mass in kilograms. Our third step is to insulate the block. This can be done by coating it in an insulating material, such as a sponge or cotton wool. This will help to reduce the loss of heat to the surroundings. Our fourth step is to record the temperature of the block. This is done at the start of the experiment in degrees Celsius. Next, we need to attach the immersion heater to a joule meter. This will measure the amount of energy supplied to the block throughout the experiment. Our sixth step is to switch on the immersion heater to start heating it up. Now, we need to wait until the temperature of the block has risen by 10 degrees. The heater is providing thermal energy to the block, which we can measure using the joule meter. We can measure the temperature of the block using the thermometer. We now need to measure the final temperature of the block. Now, we can find the energy and the temperature change. We should make a note of the final temperature change and the final energy value on the joule meter. Our equation for specific heat capacity is delta E equals mc delta T. In order to find the specific heat capacity of the block, we have to rearrange to make our specific heat capacity the subject of the formula. Therefore, as we can see here, this is the rearranged equation. Now that we have our equation, we can put in the values we have recorded. Our value of delta E will be from the joule meter, m is the mass of the block, and delta T is the temperature change that we measure. Once we have calculated the value for specific heat capacity, we have to give the correct units. Let's quickly recap the steps we've just learned. First, we need to take the block of material. Then we need to measure the mass of the block that we've taken, insulate the block, and record its temperature. Next, we need to attach the immersion heater to a joule meter. We can heat the block up using the immersion heater. We can now find the energy and the temperature change using the joule meter and the thermometer. We can rearrange our equation to find the specific heat capacity and substitute in our numbers. Finally, we need to ensure that we give the specific heat capacity in the correct units. It is really important to understand the energy transfers going on here. The electrical energy from the power supply is going to be converted into thermal energy in the immersion heater, which is then going to be converted into thermal energy in the solid material. In exam questions, you might be asked to interpret the results from this kind of experiment. Even if the question involves different materials, the basic principles will remain the same. It's essential that you learn the method that we've just been through, as this could also be asked in the 6-mark questions. We've now covered all the specification points for this tutorial. Feel free to skip back through the video and re-watch any of the sections you might be unsure about. We have now completed Lesson 3.